We are here. We said AI, we said quantum, we say it 3 times. We turn into a fish or something. This is a nerve-wracking panel, to be frank with you, because there are some pregnant expectations. When you say certain words in the Bitcoin space and people lose their minds immediately. And we have an opportunity here where we have to cross a chasm. And we have to cross a chasm between some of the smartest people you know, computer scientists, academics, engineers, and then us, the Bitcoin miners. So what we have here, I want to set the stage, and then I want our brilliant guests to introduce themselves and to give us some context. But I want to set the stage that that's our challenge. And us, the knuckle-dragging Neanderthal Bitcoin miners, are going to do our best to not jump on anybody. Everyone will remain in their seats for all catchphrases or all things that are said. Because we want to hear what you've built, what you're innovating. We're going to preface it that you're not here to sell us something. You're not here to tell us that we're all going to burst into flames, that our industry is doomed. You're here to articulate to us that you, academics, engineers, brilliant folks, have developed something that can be very, very consequential for us, but we have to bridge that gap between the academic, between the conceptual, between this really hard computer science problem, and between us who just want to plug it in and make our magic internet money. So with that, we're going to behave, all of you. I'd love for you to introduce yourselves, and then we'd love to jump into what this innovation is that we're talking about today.
Awesome. Thanks, Rob. My name is Jose Rios. I'm the former VP of blockchain stuff at Intel. We created that first chip at Intel, Blockscale, that now has been kindly donated to the foundation. But then we got hit with the crypto winter and then the Intel winter that was still going on. And they wanted out of Bitcoin. But I didn't. I made a lot of friends in this industry over the last 5 years, and that's why I'm still here. During that time, I met Francesco. I've been advising his company and others, and I'm doing a startup on AI and crypto and other stuff that's not for today, but we have some interesting research to share. And I also want to share the story of Blockscale and how we did some of these chips before, because I think that's kind of a fun topic that we can all appreciate. So
brilliant.
Okay, I'm Francesco Gardin. I'm theoretical physicist by education, and then I spent all the rest of my academic life in AI and theory of computation. And I represent a small investment company, an R&D company in London, listed on the London Stock Exchange. And we started with a very negative experience back in 2017 when somebody suggested on the board that we should invest in Bitcoin. And so we engaged a data center designer and engineer, and we built our container, which we ship in Serbia, right at the border with Kosovo, where the war just ended. And that's the beginning of the end. And what really shocked me at the time is where can we add value? Because we buy the machine from the same suppliers. We can only try to find cheap sources of energy, but that's it. And I refuse to think of a business which is basically dictated by the supplier of the hardware. And then I thought, we must do something. We should be doing something to improve the situation.
Let's do it.
Let's improve the situation.
So there's a claim that I'm sure if you've read your Pertalix link that has the description of all the panels, of a discovery of some technology, of some computer science that you've done, that we are now proposing is giving us a 30 to 50% efficiency improvement on this thing that we've just been banging our heads against for over the last decade. That's pretty big.
Yes.
Let's talk about it.
Okay, so back in 2021, in February, with my partner in crime, Rita, who's a former professor of AI at Milan University, we just finished a project. We filed a patent application, which has been granted in December 2023, on how to train bacteria to do problem solving. So very challenging project. Took us 2 years. And then at that point they said, okay, Rita, we have to give it a try. So in the meantime, after the disaster of the container in Serbia, I started to study this algorithm, which is SHA-256, and see whether there was any angle that we could attack it to make it more efficient.
And what do we mean by more efficient? Because I want to be super specific here. We spent probably 45 minutes yesterday discussing, figuring out how are we going to introduce this, and then I spent another hour talking to Mike, trying to get him to not run away from me on the bus, to help explain the same things to me all over again. What are we meaning in a very specific way? Because there's a lot of subtlety to what we're saying that we have to be super clear about.
Okay, so we wanted to take a limited risk, and so we approached the problems from several directions. One was quantum computing, and so we set up a team with an expert in quantum computing, a professor at Milan University, and we told him, okay, now you write a quantum version of SHA-256, which he did. We involved Love Grover, who is one of the most important figure in the sector. We've been using his theorem. We've been using different kind of quantum computers, from D-Wave, which is quantum annealing, to then the IBM computer, and now we have an algorithm, which we are filing a patent for it, but there is no machine where to run it.
So you've got the algorithm, you just have nowhere to put it.
Yeah, but we cannot run because we need a number of qubits which are not available and won't be available for a number of years.
And so what does this discovery set the groundwork for?
Okay, so this was just one approach. And then we took a different angle. We engaged Raoul Naik, and maybe some of you have heard of him. He is the one that in 2012 managed to reduce the 64 steps of compression in the SHA algorithm to 60. So at the 60th step, he could tell whether you would generate a winning hash or not. So we took him on board and say, okay, Raoul, now you have freedom to do whatever you want to improve and to see whether your work, he holds a master from UCL, which is one of the top universities in the world, if you can improve it. And say, okay, fine. And we filed 2 patents to improve it. Problem with improvements of, from the logical improvement algorithm to a hardware which runs it, is that an improvement on paper doesn't necessarily correspond to an improvement on hardware. So our FPGA and ASIC designer can say, okay, this is a very smart improvement, but the synthesis tool will do it automatically. But anyway, we filed 2 patents, and they are ready there if we want to design a chip. And then at the same time, we engaged 3 different AI teams that weren't talking to each other because we wanted each of them to come up with potentially different solution. We created an ideal environment for them to experiment, so a bunch of GPUs where we implemented the SHA-256, where you could do basically whatever you want. You could stop at some point the computation, you could reverse computation, and that was the experimental environment. And all of 3 teams came up with results which prove that you can beat SHA-256 in the sense that you can run it more efficiently. And the reason we believe this is the case is because SHA-256 has not been designed to mine Bitcoin. It's been designed for a very different reason. And its use is against its nature. There is sets of syntactic rules that are imposed to mine are gives you the opportunity to exploit the redundancy.
So that preface that you give, I think, gives us some good context where there was almost a computer science solution that says instead of running these 64 cycles, we're going to run 60. It becomes known. And now, does that discovery now become built into every subsequent chip because it's sort of a known solution? Are we suggesting now in the same way that what you're saying that these teams have found are these discoveries that will wind up being pushed to silicon at some point? Where are we in this world? How do we understand the application of this? Because it's a claim. It's a big claim.
Yeah.
And you're coming at it from an academic sense. You're coming at it from really deeply understanding the mathematics of it. How do we close that chasm to application?
Okay.
Are we close? Are we far?
Of the three different approaches, which are method A, B, and C, which are totally different, the closest one is method C, where we have trained, and it took us more than 2 years, an AI model, and we have fed him with the trillions and billions of data. We have 2 petabytes in our data center, where we store all the data of this run of the ASICs and the GPUs, and we have generated an oracle which has the ability to basically tell you in advance, before you run the double SHA, where the result will end up, whether it will be above or below the target. And that for us is good enough. So we're not beating SHA in the sense that we're not doing something different, but we are giving an assessment of where the computation may end up. And that's good enough for us to perform the computation if we know that it will end up below the target, above the target.
So this argument, the efficiency gain that we're making the claim about, instead of saying something like, we figured out a point in the mechanical process to go left instead of right, or to cut this piece off, what we're saying is, we know the mathematical search space of SHA-256. What we're saying on the entry point, before we even go through the mechanism, you're making a determination that says, well, we can eliminate some of that mathematical search space.
We can avoid to feed an input, which is an instance of a header, to SHA, because it's very unlikely that we'll generate an hash above a certain level of difficulty. Now, one thing is to have the oracle, the other thing is to have an efficient implementation of the oracle. So 2 weeks ago, we filed a patent, which is an efficient implementation of the oracle on a chip, because you want the oracle to be very fast. You want oracle to use a minimal amount of silicon, which is between 1% and 4% of the silicon needed for the double SHA lane. And you want to be so fast that all the lanes on the ASIC will always have an input to process. Because if they don't, then there will be a bubble going on, and that's inefficiency. And that's where we are now. Unfortunately, the only way to experiment in real time is with an FPGA. FPGA, although we have a large FPGA, but we can only implement 6 lanes plus the oracle. But that's good enough for us to measure the performance of our oracle.
Is anybody else freaking out right now?
A lot of people came to me with tricks while I was at Intel to improve this situation, right? And most of us in this room use physics. Whether you cool something, you remove heat, you save money. You run it faster, you save money. And at Intel, we did a lot of work on the circuit design, so we would, no pun intended, short circuit the whole thing, right? Mm-hmm. And but people would come from, people that work at Google or somewhere, and on the side they were working on breaking SHA-256, and they would come to us, and I would be like, yeah, right, whatever.
Sure.
So I work in a big place, and I had a big team, so we always could put a person or two on this and kind of like go figure it out for a month. And most of the time we'd come back and say, yeah, there's nothing there, or it's so complicated that, it will be more work to implement it than the savings you would have. Yeah. So we always would focus on the nanometers of the chip, and the smaller the chip lithography, you consume less power, and that would be kind of the order of magnitude effect we would have over time. We started to play with these things at Intel in 2014. A Bitcoin mining chip in 2014, that's kind of weird. everything was Chinese stuff. The only person we knew doing that was Marshall. He's somewhere in the room, right? So Marshall was an original consultant in that project. We called it Yerba Canyon. It was running on 14 nanometers in 2014-15. And we put a bunch of them to test it. There was 5 petahashes, Marshall, I think. Right? I don't know if he's in the room. There's a couple of former people from my team here, Ronald and Gary. And at some point, 10 years of doing that stuff, Bitcoin would go up and down, and when it crashes, then Intel would cancel it.
The
and
interest
like
rises,
yeah,
the
everything.
interest falls.
Yeah, just because a big company was not into it, right? We always have to be swimming against the current. Actually, they wouldn't even let us put the 2014 5 petahashes on a pool. We would be, we actually mined a simulation to test it on a non-public pool. So we mined. Later we did the math. It was $600 million when we did the math.
Intel.
But nobody was going to let us connect an Intel computer to a Chinese thing for funny internet money. So you would get fired on the spot. And we did that math when we closed shop. Bitcoin was at 50,000. So now I don't even want to think about it. But
yeah.
So long story short. We canceled that. Then Bonanza was another project that came from the factory where Gary's working and Ronald. And this is the actual chip that was donated to. This is a small ASIC. And maybe we can pass it around because people can appreciate the size of these things. An ASIC is an application-specific integrated circuit, right? ASIC. A lot of people know that, but a lot of people, when I came into the space, would call a machine an ASIC.
That's right.
And I was always like,
we still do.
It's
We're
not
sorry.
an ASIC. Yeah, but anyway. So hopefully now you see what an ASIC looks like, and then we use the proper nomenclature. But at the end, we built the Bonanza 1, the Bonanza 2, and then the crypto winter happened, and then the Intel winter happened.
Yeah.
We lost a lot of money there, and we sold a lot of that stuff. And thankfully, the folks at Block have a vision, have a long-term vision. Is not a management team that you have to convince about Bitcoin. I used to work. The CEO of Intel, when I first brought the project, we were already working on it for 4 months, and he called Bitcoin evil. So I was hoping to get away with it and kind of apologize later for it, but at that point I knew we had to turn it around. So we did a couple things to get it out there. But when I was closing the shop, Francesco shows up and says, hey, we have this thing, and the best way to implement it is inside an ASIC, because we can put it in the miner, we can put it in CG miner, we can put it in the pool, but the most efficiency would come if we could truly put that prediction engine right before the SHA engine takes over. So I've been kind of working with him a little bit outside during the last year.
Because this is the question, as I can see the thought bubbles above every single one of your heads. This is the question in everybody's mind, which is, okay, if it works, we press it to silicon, and then what happens next? So we've almost closed the chasm between us knuckle draggers and the computer scientists. But what does this mean? What's next for you? Where is this? Because you don't have the product per se. It still needs to be pressed to silicon. But what are the next steps? What's bringing us closer to what we're all envisioning, which is, I'd really like a machine with that.
Okay, so the only way to use effectively our Oracle is to have it on silicon. However, I cannot promise anything, but I can only share with you that now we are training our AI models to operate with what we call meta headers. So not a specific instance of a header, but part of the header. And if that works, then we can install our Oracle on ESP miner, CG miner. It will be less efficient because he has less information about the header because he's making assumption on a block of, say, 256 bits, which are unknown. But still, if it works, we could make it available as an upgrade to operating systems of miners.
And so, what do you need most next? Because these are not short processes, and these are not cheap processes.
What we desperately needed, was the Intel chip, because this is, I mean, the Oracle of Method C, But we have method B, which has even a better performance. But when we train it in the lab on GPUs, it was perfect. Then, and this method basically guides the search of it doesn't filter, but it guides the search of SHA. But the control, the ability to control every single bit, every single step of the computation which we had on the GPU, when you use a BM13XX family ASIC, you lose this control. I mean, when you have in one of the early ASICs, the BM1397, when you have gaps in the known space, why there are gaps in the known space? I mean, the known space should be 4.2 billion possibilities, and you have only 2/3 of them. So why did the designer of that chip decided to make holes in the known space? And this is destabilizing us because we made assumption on a chip which will roll every single element of the known space. Why do they, in the new chip, we can understand why they do it, but why they put the ability to have 16 versions running in parallel. So these are all technical problems which make our methods more difficult because we have to adapt them to the chip. And in the case, and that's why we approached in 2022 Intel, their chip would have given us the ability to have all these controls. So we are really looking forward to Scott's project to make the chip available on BTAX.
Yeah. But in general, since they just filed a patent, we are glad to bring it to this community, to throw rocks at it, to challenge it, to collaborate, to bring it from the lab to production somehow, because we cannot do it alone. I don't have a fab anymore. I quit when they said no more Bitcoin. I said, I like Bitcoin. I'm quitting with it.
For you. Congratulations. I want to make a note here, and then I want to ask a final question before we go into questions. But there's one thing that we're, first off, very, very fortunate to have you here. We couldn't be happier to have you at the park, to have you willing to show up and share your discoveries and the research and the things that you've been working on here. We're nicer than we look. We're quite nice.
Yeah.
It's so bizarre to me that the same problems that you're running into as career engineers, theoretical physicists, academics, are the problems of an open source community of tinkerers.
Yeah.
You have the same problems as Schnitzel, who's probably still sitting in his hot tub outside.
Yeah.
Oh, he found a towel. Good. But I want to put a pin in that so much to say that it underlines how important spaces like this are. And you might not have realized outside of the circles that you were in that you were solving for a lot of the same problems that we are here. So I'd love to ask a final question of you both, and then I'd love to open up the conversation for audience questions. I do want to make a note, too, that we said that they have a beautiful slideshow to go through that's substantially more technical, that they would love to kind of walk through. Outside of here, if you want to get into really technical weeds, you've agreed that you'd be interested.
Yeah.
They'd be happy to sit down, kind of walk you through and look at these details, because I know some of you are just like chomping at the bit to really look at the numbers. But the final question that I want to propose to y'all is, how do you see this? Do you think about the downstream effects on our industry? Because I'm sure that there are many. You're so hyper-focused on these very technical problems that you're solving for as you work through the method. Do you think about how we are going to receive you? Do you think about that kind of grand scheme, or is it just another day in the data science world for you?
No. I mean, I'm a physicist, so I believe in numbers, and when I see numbers in the lab from the experiment, that's it. We can look at them from different perspectives, we can share with colleagues, but numbers are numbers. But then these numbers have to show their effect on a silicon chip which has been designed by someone else, running on an operating system which has been a mess. We never thought that we would end up with 3 people becoming super expert on CG Miner, in order to control and guide the chips. So this journey has provided us with a lot of unexpected situation, which we had to cope with and to hire the right people. So we are as eager as you to make these results available. Of course, we are a commercial entity, so we have also purpose. But knowing that in the lab you have the confirmation and not being able to deploy it in a real situation is really devastating.
What do you say, Jose?
From my point of view, I think we're blessed that we have big companies that invest a lot of money in this stuff and that have the vision, like Block, right? Long view on things. And then we're also lucky that there's the open source stuff. Open source for the win. Right? Think about it as changing the world. It's really the long-term way to do anything. It's rocking the AI world, right? The internet runs on Linux, not on Windows, right? It's just so basic and so obvious. So to me, what you're doing here is helping that. And you need more standards, more, the foundation stuff is more than regulation. Of course, we're scared about that. Thankfully, not over the next 4 years, but we need more standards, right? The crypto industry or the Bitcoin industry, you can thrive more on that. And we did it for the PCs, right? PCs wouldn't exist and ship in the millions if there was no USB and PCIe. And so we cannot let Bitmain you dictate the size of the fans and the shape of the cables. We can do better. So I think this is the mission for everyone.
Can we get a massive round of applause? Thank you so much.